In this video, we're going to talk about Voronoi diagrams. Voronoi diagrams is a really cool application of linear functions, and we're going to see how we can create a big piece of art, such as the one you see on the screen, using our knowledge of linear functions. In order to understand what a Voronoi diagram actually is, we're going to start by looking at 2 points. Now, these 2 points will be the center of our circle. And what I'm going to do is I'm going to start by expanding each circle so that the radius gets bigger and bigger. These are going to be called sites. At some point, our 2 circles are going to be expanding in a way that they're going to be touching each other. So they're going to be intersecting. And at this point, when they're intersecting, it creates a straight line, which we're going to be calling our edge. And it's going to be a line created by expanding these circles at the same rate. Therefore, this edge is always going to be the same distance away from our center of our circles. Now we're going to apply this concept, but with many different sites, many different points. And when we expand them, we get a beautiful pattern, which is called a Voronoi pattern. And we're going to talk about each parts of this Voronoi pattern. This is called a cell, and we have sites, which are points. These are called the edges, and like we mentioned, each edge is equal distance away from the site itself. At this point, which is called the vertex, we are intersecting 3 edges together, and this means that we're equal distance away to all the 3 sites that are created by this vertex. Now that you saw the animation, let's talk about the vocabulary that we're going to be using in order to differentiate different parts of our Voronoi diagrams. The first one is sites. Sites are the original points in which we are creating each of the cells. Each cell is going to have a specific site in the middle. If we talk about the cell, a cell is going to be the whole section that your site is in. So the cell of A, for example, is going to be all this yellow highlighted, right? Then we're going to have our edges or boundaries. Our edges are what's created when 2 cells are touching each other. So here we have the edge between A and E, the edge between B and D. And the last important key vocabulary for us will be a vertex. Now, a vertex happens when edges intersect. So at this point here, we have the vertex that is going to be intersecting because it is going to be intersecting the edge AE, the edge AC, and the edge EC. So this is the important 4 words that we need to know when we're dealing with our Voronoi diagrams. And we're going to be using these a lot. Now, this was touched upon a little bit in the animation, but I just want to make sure that we understood what is happening when we do in fact have a vertex. So when we have a vertex like this one, which is the intersection of this edge, and this edge, what it means to be at a vertex is that this point here is equidistant, the same distance from O to C as from O to A and as from O to B. So all of these, I'll draw the line a little bit better between O and A. All of these are equal distance to each other. So if I could draw 2 lines to represent that they're all the same distance. And that's the important part of understanding what a vertex means to us. Let's do an example. How many cells does this diagram contain? So cells, we have our cell A, B, C, and then we also have the cell D here. So this would contain 4 cells. How many vertices does this graph contain? Vertices are the intersection between our edges. So we have 3 of these vertices. Identify the sites that are closest to these points. Sites. Okay, let's look at the first one, 2 and negative 3. 2 and negative 3. This point is in the cell B. Therefore, the closest point to here is going to be B. If we look at 1 and 5, 1 and 5 is here. Since it's in the cell A, the closest point to this one is going to be A, the closest site. And then our final one, negative 1 and negative 2, negative 1, negative 2. Now, negative 1 and negative 2 is on the perpendicular bisector between C and between D. So since it's on the perpendicular bisector, that means that these two distances are exactly the same. So for point negative 1 and negative 2, there's two sites that are the closest. D and C are equally as close to this point. Next question. What can we say about points that lie on the green edge? The green edge, you can see it up here. Well, this edge was created because it's the perpendicular bisector between A and B. So if you would continue this line straight, you would notice that in fact it does perfectly intersect A and B perpendicular, right? So it's a perpendicular bisector. So what does it mean to be on this line? Well, it means that we're equal distance away from A and B. And we've been talking a lot about how do we construct the edges, and I've been saying that it's perpendicular bisectors. So like we studied last class, perpendicular bisectors are going to be how we calculate the equation of each of our edge. So we have 2 points which will be given to us, and we're trying to find what is the equation between these 2 points, which is our perpendicular bisector. So all of our knowledge from last class will be coming back in our Find the coordinate of the missing site. So what we need to notice is that in each cell, we need to have one site. So we have A, B, C, D, and then we have this cell, which is created by the perpendicular bisector of D and whatever this point is. We have the perpendicular bisector of C and whatever this point is, B and this point, and then we have A and the point. So these 4 edges create a cell, and we're missing a site. So we need to find what is the missing site. Well, what we know is that the creation of the cell itself was based on the perpendicular bisectors. So I can look at, for example, point A. And the reason why I want to look at point A is because the perpendicular bisector is a horizontal line. Therefore, what's perpendicular to a horizontal line? Well, that's going to be a vertical line. So if I draw a vertical line going down from A, this would be the line connecting point A to, let's say, point E. Let's call this cell E. And since we need to have a perpendicular line between each sites, well, I can see that from A to the perpendicular bisector, we're going down 2. And this distance needs to be the same as on the other side. It's like a mirror image. So that means that I know that my point E is going to have to be this coordinate, which is the coordinate -3, -1. And to check that you did this correctly, you should be able to draw the line between E and D. And this does look like our section here is equidistant to D, as it should be. And then you could repeat the same process from E to C and E to B, and you'll see that you have the correct point for E. There's a concept in Voronoi diagrams that's called the nearest neighborhood interpolation. And this is just a really fancy way of saying that whatever cell you're in, you're going to assume the value of whatever site that is. So if we look at the example to try to understand what that means, Ted measures the rainfall in his city at 3 locations, A, B, and C, that are marked on the map. So our map is here below. The results are shown below. Location A had 12 millimeters of rainfall. location B 7 millimeters of rainfall, and location C had 15 millimeters of rainfall. Using the nearest neighborhood interpolation, estimate the rainfall at each of our points. So we're going to look at where these points are. -4 and 1 is going to be here. -4 and 1 is in the cell C. Therefore, the site C is the closest to this point. Since it's the closest to this point, we're going to assume that whatever rainfall fell in C is going to be falling in this point as well. So estimate how much rainfall. Since C got 15 millimeters of rainfall, then that means our point -4 and 1 is also assumed to have 15. Next up, 3, -2. 3, -2. Now 3, -2, the nearest site to this point is B because we are in the cell of B. So B had 7 millimeters of rainfall. So it's assumed that at this point, we're also going to have 7 millimeters of rainfall. Our last question is 1 and -1. 1 and -1 is actually our vertex. Now this point is equidistant away from site C, A, and B. All of these are all equal distance. So that means that since we're equidistant, it's going to be the average of all 3 points. So what we need to do is we need to add up all of our numbers and then divide it by 3. So doing the when you take the average and do this in your calculator, you'll get that the estimated rainfall is 11.333, so I can round to 11.3.